Okay, anybody have any questions from before? We've been talking about casting, and we're trying to impart geometry, structure, and homogeneity. And the last time I spent a lot of time on continuous casting. I guess what I want to say about continuous casting right now is the problem with continuous casting is it's a process that's too productive. A big plate mill continuous caster where you're casting something that might be 6, 8 feet wide and 10 inches thick, and the continuous caster will do 3 to 5 million tons a year. Well, there's not that many places that need or have that much hot metal to be able to cast that amount of material. So continuous casting is something that, I'm going to give you some examples in the copper industry of there's only so many continuous casters, big continuous casters you can tolerate in the world. You can make small continuous casters, and I passed this around before. This is a piece of copper that was cast from a continuous caster, and the continuous caster is about half the size of this room. It's not very big, okay? And you can make bar. I think this is 1 3/8 diameter originally, and they were just going to turn it into electrical wire. Well, there's lots of electrical wire, and so you can cast this, it kind of comes out at a few inches a minute out of the caster, and then if you draw that into wire, that's a lot of miles of wire so far as that goes, but you got a lot of one product. Now, there are certain industries like the automotive industry where you have lots of volume and things, and you can use something that's a continuous production mode. But most things, or many things, you really can't. You can't absorb that much of something. The nice thing about, or one thing about continuous casting, we're producing simple geometries, rods or plates or something like that. I did show you the I-beams, and that continuous caster is about 2 or 3 times the size of this room. A big plate caster in a steel mill is half the size of this main complex of buildings, okay? So there's all kinds of different sizes of things depending on what you're trying to do. The other thing about casting is if you're extracting the heat of fusion, we talked about as you get to larger sizes, much more than a foot in diameter, you're talking about hours to extract the heat. Now, we also, and we'll talk about it a little bit later as we get down to structure and homogeneity, sometimes we like to cast things very thin, and I used to have some rapidly solidified amorphous metal, and if you cast it paper thin, and we can talk about that in a little bit, I couldn't find my amorphous metal sheets, but you cast it paper thin, you actually can make it extremely homogeneous. You can make it essentially as a glass. And so there's everything in between, and it depends on what people are trying to do. Now, so section size is one problem with extracting the heat of fusion. Another thing that people do is there's undercooling. And undercooling is basically the situation that if you have some temperature versus time and you're extracting heat, if this is the melting temperature, the thing should solidify here, but in fact it won't nucleate, and it may go down in temperature, it may remain a liquid down here below the melting point, and then when you finally do start to nucleate, it will, as the solid starts to form, it gives up the heat of fusion, so the thing heats up and it ends up on a cooling curve like that. So you get undercooling below the melting point because of this barrier to forming a nucleus of solid material. And that's because the solid material has a certain surface energy, and we don't necessarily want to turn this into a course on nucleation and growth, but you have to form some solid particles to start growing, and you need a little bit of energy differential, a delta T of undercooling to do that. Now, people have tried, NASA spent all kinds of money because it justified doing some experiments in space, and they just wanted to prove that they could spend money in space. and tell Congress it was science, but let's see. See if I can find my undercooling curve. Anyway, the more you undercool something, you'd like to undercool it such that the delta T, this would be delta T here, if the heat of fusion is less than the heat capacity delta T, then you basically could undercool, and when you nucleate, you could solidify the whole thing all at once, instantaneously. And it turns out that they've done that, but only for one element in the periodic table, and that happens to be phosphorus. And now I can't find my phosphorus undercooling slide, but anyway, I'm sure I'll find it eventually here. Maybe we'll have to come back to it, but let me just check. I lost it. Oh, I put it at the back at the very end. So this actually is a plot of melt supercooling, where you undercool, and it's normalized to essentially this delta T equals to the heat of fusion. When you're below 1 on the normalized curve, you're hypercooled, which means you've extracted more heat from the liquid than the heat of fusion. And the reason we can do this with phosphorus, phosphorus doesn't have a very big heat of fusion, doesn't take a very big delta T. In fact, the delta T here is on the order of 20 degrees or so. But anyway, the velocity that the solidification occurs ends up getting up towards something not equal to the speed of sound, but something fairly fast. Actually, it's not close to the speed of sound. But anyway, you actually cool, or you freeze very rapidly when you don't have to extract the heat of fusion. Now, one thing that was developed at MIT is a shape casting process where essentially they extract about half of the heat of fusion. This is a genealogy, you don't have to read it all. Shape casting processes where you use a metal mold and high pressure die casting. This whole thing is called semi-solid processing. What do we mean by semi-solid? You ever had soft serve ice cream? That's semi-solid. It's about 30% liquid, it's about 70% solid. Little ice crystals. You ever had a Slurpee? Okay, at 7-Eleven? Okay, that's about 50-50, 50% ice, 50% liquid. Okay, it's a semi-solid. It's partly solid. So, you know, your Dairy Queen soft serve ice cream is actually liquid and solid ice crystals together. Well, it turns out Professor Fleming's here back in 1970 had a student trying to do a fundamental study of solidification, and the student ended up writing up his doctoral thesis, going off to spend his summer for a couple of weeks with the Army and reserves, and turned in his thesis thinking that back then you didn't have word processors, that Professor Fleming's wouldn't have the heart to change very many things. He'd be able to come back from his summer camp with the Army and graduate. Well, Fleming's looked at it and said, this isn't a doctoral thesis, and threw it back in his face when he got back and said, start all over again. And at that point, they basically changed the experiment, and a year later he ended up with what's called rheocasting for rheology. Rheology is a study of fluids, and essentially they would cool the liquid down and they'd stir it, just like you make soft serve ice cream, okay? And they were doing this on lead tin alloys, but they showed they could get unique structures, and they've already extracted half the heat of fusion. And so They thought this would be great for die casting, where you inject the metal into a solid mold, you just push it in with under pressure. And the problem in die casting is your cycle time. You've got to push it in and hold the pressure on there until the thing solidifies. The bigger the part, the longer it takes to extract the heat of fusion. If you've already gotten half the heat of fusion out, you can cut your cycle time down by half. So if they look at high pressure die casting, and there's this whole technology of recasting. It's a slurry thixo casting where you essentially freeze it hard, but you've created a structure that it turns out when you heat it back up, you can end up with a recast type of structure. And thixo molding, where you actually end up with something that's soft, and if you use dyes at the same temperature, you can actually mold and get a shape to this stuff, kind of like playing with Play-Doh. That was all developed here at MIT. I was the student who helped the guy finish his first thesis. I left after he got back from summer camp, so my name is not on the patent. Okay, I was an undergraduate grunt for him. If I'd stayed working for him for another 6 months, I would have been the patentee of all this. This is also an example of MIT's big mistake in patent technology, because they patented it to a company that sat on the patent for about 10 or 15 years and never did anything with the technology. And this is actually why MIT changed its whole patent position in the mid-1980s, where essentially MIT, if they license a patent to somebody now, to some company, they have march-in rights. If you don't do anything with it, they'll take the license back and give it to somebody else. Because this technology lost about 10 or 15 years because they licensed it to a company that didn't want to see it come to market. And they're, because it was competition for them. So the company licensed it to keep it out of the marketplace. So MIT learned their lesson on that. And so MIT didn't make any money. Other people make a lot of money. And in fact, today, there are a lot of automotive parts that are made that way with recasting, where they've already extracted half the heat of fusion. But if you have a fancy Canon single lens reflex, they have a magnesium body. Okay, it's a black camera body, but inside is this very thin-walled magnesium housing to make it nice and lightweight. That's recast. And the reason it's recast, if you've extracted half the heat of fusion, you've also gotten rid of half the shrinkage. And so you can make finer parts, thinner wall parts, okay, so far as that goes. So the technology is used a number of places, so far as that goes. So in casting, we're trying to impart some sort of, we talked about continuous casting, and I may talk about a couple of those, but in general, we're trying to impart some sort of shape. And we've got this problem of shrinkage over here, and this shows a casting. Just to cast a part like this, you may have to have a mold that's 3 times as high if you just cast the thing into a sand mold. Quite often for steel or cast iron, people used for thousands of years sand, silica sand, that you form the shape of the part you want to make, but you have to pour in this extra metal. Initially you pour it in liquid all the way to the top here, but because of shrinkage you get this pipe. It looks a lot worse, but if this is a cylindrical part, the void volume in the center is small as you're shrinking the radius down to 0, but you can end up with a pipe that is deeper than the actual casting. If you do some other things like put a chill block in here so that you extract a lot more of your heat from the bottom, you actually can get rid of a lot of that pipe. And so you're starting to shrink here, and so a lot of the volume here of this is the same as the volume of that. Remember, you got this radius thing you got to worry about. So the area of the volume out here at a large radius is much greater than the volume of that area there, okay? It's RDA, if you will. In any case, if you were to cool entirely from the bottom, all you're going to do is push all your shrinkage up to the top, and you'll have a very flat surface across here if you think about it. So by putting chill blocks into the sand mold, you can change the amount of what we call risering. In the casting foundry industry, this thing above the actual part is called the riser. You're going to cut the riser off and send it back to be remelted. But if you put in chill blocks, you don't have to have anywhere near as tall a riser. Okay? You also can improve the structure. So they also put in things like hot tops or radiation shields on the top so that you get a little bit more one-dimensional heat flow, and you'll get here you have a chill block with a shorter riser, but if you put a hot top on here, you actually can get a very small riser, and if you put a radiation shield up here, you can get things very flat. Anyway, you can change the cooling on these complex shapes by playing all kinds of games, and we do, okay? But a lot of, well, actually today, computers are fast enough that you can calculate these things. 25 years ago, people couldn't calculate. It was kind of too complex a problem. The heat diffusion problem, where you have a step in one of the properties, for all you mathematicians out there, and you're all mathematicians this summer, if you look at the heat diffusion, or the enthalpy versus temperature, as the metal heats up, it gets to the melting point, and then you have this step, which is the heat diffusion. And this is the enthalpy of the solid, and this is the enthalpy of the liquid. The slope of these things is what? Anybody remember from your heat capacity, or from your thermodynamics? It's heat capacity, I just said it. Okay, the slope of the enthalpy versus temperature is the heat capacity if you ever took thermo. Anyway, and so these have slightly different slopes because the heat capacity of the liquid is different than the heat capacity of the solid, but this heat diffusion, this discontinuity, mathematicians don't like. And in fact, it's called the Stefan problem, after a mathematician named Stefan Boltzmann constant, Planck radiation. The Stefan did work on that. But anyway, that creates a problem for all the computer jocks, okay? This discontinuity. But it's a real problem, and so computers were not powerful enough 25, 30 years ago to really handle that problem very well. Today, they don't have a real problem. Okay, they can handle it. Still not easy. Still a lot of computation to handle that problem, where you have an isothermal hold, so far as that goes. Anyway, there's lots of things that people do to improve the heat flow and to try to do something about the undercooling. Or undercooling is one way, rheocasting is another. One of the most complex casting processes is investment casting, and we make some of our most sophisticated parts this way, even today. But in the old days, it was known as lost wax casting, and it's been used for about 3,000 years. So if you can make a part out of wax, and you can take wax and you can carve it. I made my wedding bands originally for my wife and myself by lost wax casting. I just turned some wax on a lathe, took it up to a dental shop where they make little bridges for people's teeth, and they had a lost wax caster. I paid the guy 20 bucks and gave him the platinum alloy I was making. He didn't have that in stock. And he cast a bunch of wedding bands for me. In fact, I have a couple of spares, okay? I figured we might get...
The video's rolling, I don't know.
Now my wife has a couple of the spares too. I figured as we got older, we would gain weight and our fingers would get fatter, and so I made them of different size. So anyway, but lost wax casting, essentially you make a wax part. Today, we actually have a permanent mold which you can machine some complex shape, and you inject wax in there. So you can do all this at, less than 200 degrees Fahrenheit. You pop the wax part out of the mold. You now basically take some wax rods and stuff, and you put these little parts and wax and you weld them to the other wax. And so you go into one of these shops and you'll see a bunch of women. This is handwork, and women do better with handwork than men, okay? And they take little hot knives and they basically just weld with wax, the wax to the wax. And they weld it up, and they'll make this little Christmas tree of parts with a riser or sprue, they call them sprues also, which is where the metal's going to go. This is inverted upside down. You're eventually going to flip it over, and you will eventually pour the metal in this way. But initially, you just dip it into a very fine slurry of a ceramic powder. It literally looks like flour, but you mix it with some alcohol or something else. You dip it in, and I was looking for my newer brass rat this morning. That's where I saw some of my old wedding bands, but I couldn't find my older brass rat. This is the big brass rat I think I passed around once. This is lost wax cast. My class ring, any of your class rings, were also lost wax cast, or what we call today investment casting, because you're going to take the plastic or the wax part and invest it in a layer of ceramic. And then you're going to put another layer of ceramic, coarser ceramic, on top of that and make a porous shell. So you complete your mold, it still has the wax inside, you stick it in an oven, you melt the wax out. You can recover the wax, reuse it if you want, make candles out of it, whatever you want to do. You then put this ceramic shell, which has cavities, the shape of your part, you put it in a furnace and heat it up to bond the ceramic powders together. This might be a 2000 degree furnace, 2000 F, okay? Because this is all ceramic now, and you're gonna bond this stuff together. But the first layer was this very fine flour, and the reason I wanted to bring my latest brass rat, you can actually take, and you can read on this one, I'll pass it around, you can read Massachusetts Institute of Technology across here. But even the one that fits on my hand, if you take a magnifier, you can read the Massachusetts, all the letters of MIT going across there on my actual brass rat. If you use a fine enough flour, okay, you can get very, very good detail in your part. So then you take this out of the furnace, you actually put it in a can, pour some other sand around it, just loose sand to give it some structural stability. Now you take your metal, pour it in, let it solidify. When you're all done, you basically knock the ceramic off. It's just trash now, and there's your casting. This was your original wax pattern, and this is your casting. It's lost wax. You lost the wax from the mold, and it's called investment casting. And that's how we start to make these $6,000 turbine blades, okay? And they actually, when they do it, they actually have a little ceramic mold that has the shape of the inside of this thing. So that how would you make something with an internal, this one's been cut in two, okay? So you can see the inside. But when Pratt & Whitney would have sold this, it would have been a solid part like this. They make it by the investment casting technology, and they end up with a polycrystalline grain. But then they take that polycrystalline structure that has this shape, while it still has its core inside, actually in the investment casting, it's still got the casting around it, and they actually cool it very slowly in a temperature gradient furnace. So the furnace is about the size of this room, costs about $1 million or $3 million. You can make maybe 16 of these at a time. You see in this thing they're making multiple copies. They might make 16, actually Rolls-Royce makes 4 at a time. Pratt & Whitney and GE make about 16 at a time. Rolls-Royce likes to have better control in a smaller furnace than General Electric and the others, okay? But it might take you 6 or 7 hours to very slowly cool from the bottom of the chill. We don't want any shrinkage in here. We want, as I said in the chill block before, you actually are going to pull it through a gradient furnace. So it's actually an induction heated furnace typically, and it may be 50 degrees below the melting point here and 50 degrees above, over 2 or 3 inches, you may have 100 degrees centigrade temperature gradient. And if you pull it through there very slowly, it will grow from the bottom. And you'll push all your shrinkage ahead. And you'll end up with a perfect part, if you're lucky. If you want, and this one actually is the $6,000 blades, are single crystals. They actually start out with a little wax pigtail on the original casting. In pigtail, it's actually a circle. It's a corkscrew spiral. And what happens is when you slowly start solidifying that, you actually will start with a seed crystal that has a particular crystallographic orientation, because these things are going to be at high temperatures and they have a greater high temperature strength with a particular crystallographic orientation. So they start with a single crystal they already made. They orient it by X-ray diffraction at the right orientation, and they start that, and it goes around the pigtail. And if you get a nucleation of multiple grains as they go curling around that pigtail 3 or 4 times, you end up selecting out a single grain. So when you get up here, it grows as a single crystal. Okay? And you end up with a single crystal turbine blade, which costs $6,000 a piece. Okay? After you've done all the metal finishing and everything else. And you have to, the holes in there are either laser electron beam drilled under high intensity, or you can take a plunge EDM machine and you can plunge the holes in there and cut the holes, because eventually, in order to get high efficiency in the engine, you want to put cooling air through there. The engine is operating typically today at something 3,000 degrees Fahrenheit and above. The alloy melts at 2,400 Fahrenheit. If you didn't cool it, your engine would melt. But in fact, it is air cooled. When we say cooling, you're actually using the compressor air from the turbine, which is about 1,000 degrees. So you're cooling it with 1,000 degree air, so you don't melt the blade, which melts at 2,400 but can operate at about 2,000 in a nickel-based superalloy. It's actually a fairly safe system in the sense that if you lose your compressed air, you've lost your turbine anyway. I mean, you can't run the turbine without compressed air. That's what the front end of the turbine is, if you know anything about turbine engines. So there's always compressed air. If we look at how that stuff fits together, we actually can make quite complex parts by investment casting. This is one where they didn't do that little seed crystal to make it single crystal, but they grew it unidirectionally, and they ended up with columnar grains. So this one may not operate at quite as high a temperature, but we've oriented all the grain boundaries parallel to the stress direction, the primary stress direction. This thing's a spinning rotor on a spinning rotor, and so the primary stress direction is radial, and we have the grain boundaries are the weak thing at high temperatures, weak part of the metal. And so we orient them in that direction. That columnar growth, well, if you went back to the 1940s and 1950s, and remember, gas turbines really weren't developed until the 1940s. And you know, the V2 rockets were some of the first, commercial, if you will, turbines. And in the late 40s, that's when jets, actually the Germans had some experimental jets at the very end of World War II, jet aircraft. But after World War II, we started building jets, and those jet engines, it was just polycrystalline cast turbine blades, or machined out of wrought material. If you go up here to General Electric Lynn, where they build these turbines for the military now, you'll see machine tools just taking solid chunks of steel and making compressor blades by just machining them from solid bars of material. When you get to the hot section, you have to use nickel-based alloys. They don't machine so well. They're very difficult to machine. And so they actually cast them. In the 50s, they'd be equiax castings, lots of little crystals. If you look at if you look at something that's just cast normally as an ingot and you look at the crystals, you would get something where you get some nuclei on the outside edge where you first pour it into the cold mold and it starts to solidify. Then you get columnar grains as the heat is flowing out to the walls. So you get columnar grains heading towards in the direction of the walls. And then the final stuff might be equiaxed. Well, in the 1950s, the standard turbine blade was just a casting, like a lost wax casting, like my brass rat, multi grain. But then by the 1960s, people were learning to cool it directionally, like using a chill block, okay? But cooling it in a gradient furnace where you have a temperature differential and pulling it through slowly. By the late 60s, people were learning to make single crystals. By the 70s, we had that kind of technology. That blade's probably about a 1980 technology blade. Today, the walls are getting down as thin as 15 thousandths of an inch. Okay, really, really thin walls. The problem with going thinner is if you have a little bit of core shift, you've got a ceramic core in the middle of that thing when you're growing this thing, and you get a little core shift of 5 or 10 thousandths, and you got no wall left. Okay, so the way they inspect those right now is they basically put them in a CAT scan machine. And for $500,000, you can buy a CAT scan machine for metals. You put one of those blades after you cast it, you put it in there, and you get a full three-dimensional image, inside and outside, just like doing a CAT scan on your brain, okay, or on your arm. Only it's designed for metals. And they do a 100% CAT scan. They measure the wall thickness on that CAT scan, and they probably scrap. Hopefully they scrap less than 30% of the production, okay? At that point, that casting, the single crystal, may be worth the actual value added of the invested casting and molding might be $1,000. The alloy may be a couple of $1,000 because nowadays we have up to 5 or 6% rhenium in those alloys. And if you look at the periodic table, rhenium is one of the platinum group metals, okay? I remember when I took my creep course from Professor Grant back in the 1970s, he came in and said, if you're gonna make a jet engine, he'd been working on these alloys since the 1940s. He says, what's the best material to make it out of? Has good high temperature strength, can operate higher than any of the nickel-based alloys or the cobalt-based alloys. And we all sat there and we couldn't think about it. He says, platinum. Okay, platinum goes to 1700 degrees centigrade as a melting temperature. You could operate platinum at probably 3100, 3200 degrees. If you want to make a platinum engine, you could get another, 1/3 improvement in your fuel efficiency of your aircraft by operating things hotter. But platinum tends to be a little dense, and so the stresses are up. It also happens to be a little pricey, okay? And if you wanted to make a really, really fancy engine, you could use iridium. The problem with iridium, they only mine about 100 ounces a year in the world. So you wouldn't make a lot of engines out of iridium. But iridium doesn't melt until over 3000 degrees centigrade. You could build a 4000 degree engine out of iridium. No one's ever done it. Well, actually, we have built iridium engines. I take that back. For these deep space flights of NASA, when they're going out to Pluto or Saturn or Uranus, anybody know how they get their energy? No, solar, you don't have enough energy density of the sun. It goes off as R squared from the sun, and it's a long way out there. I told you about the thermoelectric things, right? Well, what's the heat source for a thermoelectric flyby? Some of these things take 15 years to go out there, right? Well, they actually take plutonium. And plutonium's got a 40,000 year half-life or something, okay? 30,000, long time. Enough to go to Pluto. 10 to the 8th? Well, it depends on the isotope. Some of them are 10 to the 8th. But the worst part of it usually it'll die down to a reasonable level of radiation after about 40,000 years, as I remember. That may be a couple of half-lives, I don't know. Who knows? But it's longer than I need to wait, okay? So they take a thermoelectric generator. It's just a semiconductor, and you have to heat one side and cool the other side. It's easy to cool things out there in far space, okay? You just expose it to the, have a radiator and let it radiate out to the cold. And you're pretty cold out there. You're down, only a few tens of degrees above absolute zero. So you're cold on one side. The other side, you have a plutonium heat source. Well, that plutonium heat source is encased in an iridium shell. So they make an iridium sphere that'll go to 3,000 degrees centigrade. They put plutonium in it. They put it in a rocket and shoot it up. And they hope that the rocket doesn't fail. And they spread plutonium all over the Atlantic Ocean. But that doesn't usually make the papers that they're about to shoot plutonium, essentially nuclear warhead material, up into space. They don't do as many of those now, but it is actually a very big concern about, the environmentalists would not be pleased if they knew that you just dumped a couple of pounds of plutonium in the Atlantic. Yeah.
They would use a couple pounds for plutonium.
I don't know exactly how much, but plutonium's pretty dense too. It's not a very big, if it's nuclear warhead, they call them the pits, okay? And I don't know, but I think pits are about, I don't know exactly what the critical size is, but they're not much bigger than a walnut, I think, okay? So they had built iridium engines, but plutonium was the fuel, iridium was just a shell around it. And iridium doesn't oxidize, it's platinum, right? Anyway, so this is the ceramic core that goes inside one of these turbine blades that you're going to cast. And that gets etched out with acid afterwards. These are some compressor discs. And this is actually the RioCast technology. This actually is the finished casting. These are actually some of Professor Fleming's drawings. They're in a book now, but I recognize this. This is the firing pin for a U.S. Army, I think M16. Okay, the Army gave them millions of dollars back in the 1970s to see if they could injection mold a semi-solid steel. Okay, and this is actually injection molding. You're pressing the semi-solid material into the cavity, and the cavity actually is that firing pin. It didn't work because you didn't have mold materials that could even take those temperatures. They made some parts. They could make 100 parts on $100,000 mold. Okay, so it wasn't exactly economical. But they do make all kinds of aluminum, zinc, and brass parts by injection molding. And we make all kinds of complex parts, automotive parts by investment casting, a lot of your fuel injectors and things like that, complex parts. Oh, here's another investment cast part. Anybody recognize this? It's stainless steel. And they make another part that goes on the bottom. They weld that on. And then they take it up to a belt sander and they give it a nice finish, and you can read Spalding on it afterwards. So that's another investment cast part. Sand casting, you can make small parts. I could have brought in a plumbing elbow, a cast iron plumbing elbow. That's made by sand casting, which basically, let's brighten that up a little bit. Again. How come it's not brightening? Anyway, here it's a little bit brighter. So you start out with two core boxes. Typically, these might be wooden molds. You can shape things, and you make them in two halves that are going to go together. And one's called the cope, and one's called the drag. The drag's on the bottom, the cope's on the top. Okay, it's like book molds. In fact, sometimes they call them book molds in permanent mold casting. When you're all done, you're going to put these two things together. That gives you a cavity, or actually what you do is you get the core halves and you might make a wooden part, you might make a metal part that's basically from some of these molds in the core box. You basically then bury it in, you bury this thing in sand, but it's on 2 layers. You've got the thing, you got a piece of plywood, 1/2 here and 1/2 here, the cope and the drag. There it says cope and drag. And you'll make 2 half parts, and you'll make a cavity in the sand like this. I guess we're going this way. Yeah, well, actually, I don't know what they're doing over there. You'll make a cavity in the sand, and then you'll put the 2 parts together, one on top and one on the bottom. You now have a cavity the shape of your core halves over here, and then you pour the metal in and you make your part. Okay, so that looks like it's some sort of plumbing part or something. And we make things as cheap as a little cast iron elbow that you go to the hardware store and buy for 89 cents, right? If you buy it in volume, you get it for 29 cents.
Chinese are very good.
Chinese make a lot of these in those little kilns, those little cupolas, right? There's not a lot of people that make them in the United States anymore, okay? Now, we also make brass this way. We make aluminum this way. We make all kinds of parts. Sand casting goes back thousands of years. They just poured sand into a hole in the ground. And here, to show you a casting that was not much more, I just walked around the lab once about 20 years ago and found this. This is probably a lead or lead bismuth alloy. You can see the crystals, but you can just see that someone just scooped out some cavity in some ceramic, sand or whatever, and just poured it in. They're just trying to dump the leftover metal from a casting operation, probably. And I just said, oh, that's nice. It shows crystals and stuff. You also can make big cast iron parts that are the size of this room. If I've got a generator rotor forging, not a generator rotor forging. We talked about generator rotor forgings yesterday, but if I have I have to have a housing to put that generator rotor in. Once I take that steel rotor and I wind it with copper, then I have to have a housing that holds the other windings to make my big generator. And that generator housing is about 4 or 5 inch thick cast iron. And it's the size of a small house. And there's a top and a bottom, and it's just a big sand casting, just bigger than the little nipples that you buy at the hardware store. Okay? You also, if you go look at those nipples in the hardware store, you'll see a parting line on the actual final cast part. They don't show it here, but if this was the actual part, you'd actually see a parting line. You can see where the 2 molds go together. Okay? So, there's lots of different ways to cast things for shape. This actually is not a casting, but it shows you large grains. This is actually part of originally it was part of a superconducting microwave cavity when they were trying to generate microwave frequencies for particle accelerators for the physicists. Then we ended up using it as a susceptor in an induction furnace, and that's how it got these huge grains. The grains here are like a centimeter across, if you look on the sides of that. And then I think it looks like someone used it as an ashtray for a while. Okay. Anyway, I picked it up in the lab here once, sometime. Here's some zinc ingot, just like pig iron. This is zinc. When it comes out, there's actually a zinc blast furnace when they want to make zinc. Just like making iron ore, not quite as big in size. It may only be 2 or 3 stories tall rather than 30 stories tall because we don't make as much zinc. But they basically comes out just like the pig in the sow bar, remember? They just cast it in the sand, although in this case they probably cast it in a metal mold so that you actually would say, I don't know if this says New Jersey zinc, if it was the whole thing. I just got this because you look at it, someone just broke it with a hammer and you can see the columnar grains from the metal mold, okay? So the way you extract the heat will determine your structure of your steel or your metal, whatever type of metal it is. Now let me just finish with a couple of specialized casting processes, if I can find them. Well, why don't we take our break early and I'll find them at our break and show them to you. Oh, wait a second. Yeah, I'll find them at the break. Okay, why don't we come back in about 10 minutes, just before 8:30. just lining, it was as long as all these tables up there, and they came in one morning and they were all gone. They had been borrowed on the no return plan, right? So copper's worth a lot of money. We actually had that when they were redoing this classroom, okay, about 5 or 6 years ago. You know, there's copper pipes and things in the heating system and cooling system and stuff. And I came in one morning and, you know, I get in early, and someone was talking about they had lost $8,000 worth of copper pipe, which actually nowadays is not that much, okay, because copper prices have gone way up. And they said they didn't know who did it. I said, well, you know, I got a surveillance camera in the hall. And there is this, if you look at the fire door down there, just down from my office, I put in a surveillance camera that would watch the door to my office and the door to the lab. And I said, we never look at it unless we had a reason. But we had a reason. They had lost all the copper for this. So I asked Don Galler, the tech who works for me that took care of the camera. He's an electrical engineer, so he put in the surveillance camera to begin with. I said, go look at it, and there we had a picture of one of the contractors who had brought the stuff in. When he was in off hours, he came back to take it home. Okay, we had a picture, beautiful picture of him. So they filed suit against him. He lost his job. So anyway, okay, getting back to casting technology. So we talked about as much as I want to talk about extracting the heat of fusion. I do want to say something about shrinkage. One of the advantages of continuous casting is you don't have to cut off a riser. All the shrinkage just gets pushed to one end. And if you make something that's in a big steel mill, if you're making that casting for 3 months and you've made how many miles, you only have one hot top to throw away, or one riser top to throw away rather than thousands, right? And so you go from like a 65% yield, and yield in a steel mill is how many pounds of steel you sell out of how many pounds you cast. So if you cast 100 pounds and you sell 65, you got a 65% yield. And continuous casting took them from the 65% number up to over 90% within a few years. And as they learn to make alloy grades and other things, they actually are up around 97% continuous cast in the steel mill now. There's 2 continuous casters right down here in Attleboro. I used to work with this company that uses more gold than any company in the country, and they have 2 continuous casters. Well, in the case of gold, you want to have as little scrap as possible, so it pays to have a continuous caster. Even though you may only cast something that's 12 feet long, it might be a bar like this of karat gold, and it may only be 6 feet long. But if you only have to cut off one little 2-inch hot top as opposed to 20 or 30, it paid for itself. Even though a little caster like that might be 5 or 10 million bucks, so far as that goes. And that's how this copper was cast, so far as that goes. Now there are a couple of, and I talked about continuous casting is a little bit of a problem because it's almost too productive unless you've got a really high value added or high volume. High value added in gold, karat gold. Now a lot of those casters are a lot busier than they used to be when I started working there 30 years ago, because now they have the contract from the U.S. Mint to make the gold coin blanks. The U.S. Mint is making some sort of gold coins or something now. I don't remember. Sacagawea. Okay, the dollar. Is that a dollar or $20? I don't know. A dollar, but anyway, I guess it's plated with gold on one surface or something. Anyway, whatever it is, they have the contract to make all the blanks that are sent to the U.S. Mint for stamping to make the coins. And so they're nice and busy now. And of course, when you're making that much of something, you can use it. But they were using it even when they only made small amounts for jewelry. Although we did make a 36-inch diameter coin, 3/4 inch thick gold coin when I was working there in the 80s for the Vancouver World's Fair. They had a World's Fair in Vancouver, British Columbia, and we cast 3/4 inch thick, 6-inch wide gold 14 karat gold bars, and then I had to weld them together, okay, without distortion, and make a 36-inch diameter coin. So they had this coin on display, which is like $4 or $5 million worth of gold. Of course, they recovered it afterwards. They didn't, you know, but it was just for a display for the World's Fair for a few months. But there are a few applications of making copper. I talked about this one, but there is Southwire is a firm in, I think they're out of Georgia, somewhere, anyway, south of Atlanta somewhere. And the Southwire process is, and that's what I was trying to find, and I still couldn't find it. I must have left it in my office. There was a picture of it, but basically the Southwire process is about a 6-foot diameter copper wheel that has a groove cut in it. Okay, it's like a railroad wheel, if you will, a great big railroad wheel, and the edge of the wheel has a mold cavity in it. Okay, the diameter's down here, and this might be about 2 or 3 inches wide. Okay, so this wheel is just going to go around in circles. It's water cooled, so you can extract the heat of fusion, and they have a steel band. So if I'm looking sideways on this 6-foot diameter wheel, they actually have a steel band that goes around a roller that forms the edge of the mold. So you have a steel band right here. And this is your cavity. And they just pour copper in here. The thing goes around slowly. It solidifies, extracts the heat of fusion, and at the other end you just chop off these big sow bars of copper. And Southwire makes copper wire, okay, for overhead transmission lines and all kinds of things. There's not a lot of those in the world because we don't need but so much copper wire, and ever since fiber optics we need a lot less copper wire, okay? In fact, back in the 70s you could plot the price of a penny, and it was getting to the point, well, some of you are too young to remember, but back they used to make pennies out of copper, okay? They were copper pennies. And what happened is they were plotting the price of copper, and they knew that sometime in the early 80s it was going to cost more than a penny. There's going to be more than a penny's worth of copper in a copper penny, and they decided that would not be a good thing because people would just be melting down the copper pennies to get copper. So that's when they developed current penny. Anybody know what the current penny is? It's zinc with a copper plating, okay? Which I always thought this could have a big corrosion problems, but nonetheless, they did work that out. Anyway, because they wanted something cheaper, and zinc costs about 1/10 the amount of copper. Nowadays, they're getting to the point where the zinc penny is getting to the point where it's a little bit more expensive to produce, and it actually is costing the government more than a penny to produce a penny. So they'd like to get rid of pennies, but anyway. But in any case, this is a Southwire process, 6-foot diameter wheel, turning out kind of 2.5-inch diameter. It's actually not a circle. It's this, you know, half moon shape or whatever. But you're going to go through and you're going to roll it into a rod, and then you're going to draw it into wire. It'll produce a lot of copper for the world. Now there's one other application for copper in continuous casting. If you go up here to Burlington, Vermont, you'll find the Hazlitt Company. And the Hazlitt Company basically takes a big wide steel band on rollers, and they water cool it with a water spray on the backside, and they have another steel band coming in like this, and they pour molten copper on here, and they cast about sheets of copper come out of this thing, this water cooled on both sides, about 2 inches thick and about 3 feet wide. The steel band's about 1/8 of an inch thick. Water spray on one side to extract the heat of fusion, and you're basically making copper 2 inches thick. Now, why do we do these for copper? Copper has a very high thermal conductivity. It's easier to extract the heat of fusion from something with high thermal conductivity, you can do it in thicker sections. And in this case, they can use 1/8" steel bands. Now, it's a real mess if you break one of these bands and you now have molten copper in contact with water and you generate steam and explosions and other things. So you have to know how to do it. What are you using all this copper sheets for? Well, it turns out every copper mine, essentially, in making the copper, if they want to make really good copper, they make a copper that's got a lot of impurities in it, and then they want to go through an electroplating process. And so these are copper anodes to make really high quality copper. They essentially take big sheets of copper made by the Hazlitt process, which has got all kinds of oxide impurity and other stuff in it, and they electroplate it, and they make electrolytic, what they call electrolytic copper, sometimes called ETP copper, electrolytic tough pitch. We don't want to get into the tough pitch, but it has to do with how you deoxidize. If you go through a copper plant, actually there's one in Reading, Pennsylvania that I went through once. I had a student do a thesis down there. They actually use green tree trunks. There's lots of sap in them. And the way you get the oxygen out of the copper that you've melted is you throw a big tree trunk into the bath of copper, and it creates a boil as all the hydrocarbons from the tree trunk are boiling off or burning off, and it's called poling the bath, because you're using a telephone pole to stick it in the bath, okay? And you get this froth, and it's the hydrocarbons burning off there are deoxidizing the copper bath, okay? And I think the pitch, the electrolytic tough pitch, comes from the pitch rosins that are in the tree trunk. I'm not sure if that's true or not, but I seem to remember that from years ago. But some of this is sort of ancient technology, okay? So far as that goes. Any questions on that? Yeah.
Well, not on that.
Yeah, well, go ahead.
But as far as this one, the hazelnut process, how long does the steel band last? Are they just replace it every so often?
Yeah, every couple of days. I mean, you know, they know approximately how long they last. They've done a lot of work, and it's actually a titanium bearing steel, and I mean, they've done a lot of work on these things. I went up to the Hazlitt plant once. Can't remember why. They invited me up, and so they gave me a nice little tour. People have been trying, actually that was probably why they bought me up. The Hazlitt folks have been trying to make thin steel strip using their process, but there is no, you can't put steel on steel, and the problem is steel doesn't have the thermal conductivity of copper, and so it stays hot longer, and so you end up wearing out your bands. And you can't run a little laboratory scale one of these things. You actually have to run one that's about 3 feet wide, okay? So it's sort of expensive to do it. People have been trying to make continuously cast steel strip for 50 years, and no one's really been able to do it. They still make it as a 10-inch continuously cast plate, and they roll that down. But there's a lot of steel sheet used in the world, and if you could start it out as 1/4-inch thick strip to begin with, it'd be worth a fortune, billions of dollars if you could do it. But lots of people have tried, but no one's been successful, okay? Because it's hard. I mean, you're only working with something that melts at 2,000 degrees Fahrenheit. You get to steel, you're working with something that melts at 2,600 degrees Fahrenheit, and there's a big difference. That last 600 degrees makes things a lot harder, particularly when you're just using a steel band. And there is nothing else. I mean, the nickel-based alloys, that turbine blade, melts at a lower temperature than steel.
So use an iridium band.
Yeah, and there's 100 ounces of iridium in the world each year, and it goes for about $1,000 an ounce. Okay? So yeah, you could use an iridium band.
Or a platinum band.
Or a platinum band, okay? And it goes for about $1,000 an ounce, and there's a lot more platinum, right? You can use a rhodium band, okay? It goes for about $3,000 an ounce, okay? Yes, there are some things. Yes, okay, you're right. You probably can, but no one's done it yet, okay? So so there's a limit to continuous casting, and part of that problem is actually it's too productive, okay? Now, let's talk a little bit about structure in casting. the heat transfer across the interface, this is sort of an interesting plot in terms of distance. This would be steel, solid steel. This is liquid iron carbide alloy. We have the composition of the liquid, and we actually have a big drop as we go across here. The liquid has this carbon concentration. When you get to the interface, you go from the composition of carbon in the liquid to composition of carbon in the solid. It's sort of like the Stefan problem. You got a in this case, not a temperature discontinuity, but a concentration discontinuity, and then it drops down into here. But what you start out solidifying is not the composition of what you end up solidifying. Your liquid and your solid don't have the same concentration. And that's a function of the phase diagram. How many of you have never seen a phase diagram before? You've all seen the phase diagram before somewhere in some of your Navy training or something? Okay. So a phase diagram is nothing more than a plot of temperature versus, in this case, carbon. This is the steel diagram at high temperatures. You got liquid up here. This is your cast iron alloys over here. These are your cast steels up here. This is called the paratectic reaction. We don't have to get into the details of that. But what it shows you is the composition of the liquid is richer in carbon than the composition of solid. This is a two-phase region. This is the gamma phase. And that's generally true for any alloy. Pure copper, you don't have to worry about it. Pure aluminum, you don't have to worry about it. But any alloy that's a binary alloy, you generally have a liquid that is richer in one phase, or one component, than the solid. Okay? And that means that you get what we call segregation. So if I go back and look at my challenges and the issues, we've talked about shrinkage and how we can do continuous casting or use risers or chill blocks. We've talked about extracting the heat of fusion, and if you got really big things, you have to wait hours or days. We get down to very thin things, and we'll talk about in rapid solidification, where we melt things, we freeze things at 1,000,000 degrees per second. We get really thin, like paper thin, literally. But in segregation, what we have, when we have a two-phase alloy, we actually get the liquid that will separate to a higher concentration than the solid because of this type of phase diagram. And if I look at I can probably do it with this one. This type of phase diagram here. This is the liquid. This is a solid. This is another solid. I will always have a liquid that's higher in concentration than the solid. This is the liquidus line. This is the solidus line. And what happens is that cools down from some liquid temperature down through lower and lower temperatures. I will have a solid that forms like this, but I will get coring, and it doesn't show it very well, but you can see some kind of different colors in here. The liquid that forms will actually get a core around a rich alpha phase. And I guess what I can show you is, if you look at a real structure, this is one from one of my students' doctoral theses on stainless steel, where he used a special etchant, and you actually can see the concentration gradient of iron, nickel, and chrome. Okay? The core that's fairly white is the first FCC non-magnetic stainless steel to form, and it actually was sort of round in cells, but as it transformed, as cooling down, it actually rejected some of the chrome and nickel, and with this particular etchant it would etch a different color. Actually, originally this is in black and white now, but originally it's a color etchant. You see all kinds of rainbows of colors, but you can see in this type of picture the coring. On a microscopic scale, it's not uniform in concentration. So one of our goals was to get something that was homogeneous, and to control the structure. But depending on how we extract the heat of fusion, we can get very different structures. I'll show you some of those, and we can get segregation within the casting. Now, that casting can be on a micro scale like we see here, or it can be on a macro scale on the size of the whole casting. To give you some idea of the different types of structures that you can get, here are a number of different stainless steel microstructures that John, he was looking at a number of 6 different stainless steel compositions, but you can get all kinds of different types of structures. This is one that forms in the solid state. This is a structure from what we call dendrites. These are also some of the remains of dendrites, but you get all kinds of cast structures with different length scales, some of them very fine, we're going to talk about that, some of them very coarse. Instead of just dendritic structures, this is a similar dendritic structure. Dendrite comes from the Greek word that means trees, and this is sort of, if you turn it sideways, a tree with branches. And you can also get cellular structure, where you have cells, and the black outline, these are individual fingers of material that are growing from as the heat's extracted. If you look at it in a schematic, you actually will form 2 different phases in some alloys, and you can have cells grow where you have the alpha phase and the beta phase, or you can, if you want to talk stainless steel, that could be cells of face-centered cubic and body-centered cubic crystal structure iron. One would be magnetic, one would be non-magnetic. They can have very different properties. In fact, that's the definition that J. Willard Gibbs gave to a phase. A phase is uniform throughout in properties, not necessarily in composition, but in properties. So a phase, hopefully, is homogeneous in properties. When you have 2 phases, it's by definition not homogeneous in properties, because each phase has its own set of properties. One of them might melt at a higher temperature. If I get John's thesis out again, I'll show you where the ferrite has a higher melting point than the austenite, and it actually gets fingers of ferrite sticking out into the melt as you're solidifying. This is where you actually get a breakdown in instability called dendrites, and you can see the little branches on the trees. This is cellular solidification. This is a type of cellular solidification that we sometimes call the eutectic. It's a very fine cellular structure. So you can get, there are more cast structures than there in all these aluminum, copper, iron, nickel, titanium alloys than there really are wrought structures, so far as that goes. Actually, here's a good picture in aluminum, or no, this is lead tin. In fact, this is probably a Fleming's picture. I think this was on the cover of his book originally, okay? But these are 20%, 10-20% directionally solidified. These are probably tin dendrites growing into a lead matrix, or vice versa, I guess. It's got to be one or the other. But you can see the dendrites melting at a higher temperature. You've got liquid, the darker liquid here, and this is all solidified stuff. And you get these dendrites form in different ways. When you have a ingot casting, you actually will get the same initial nuclei forming on the outside. When you first pour it in the mold, that's fine grain. Then you'll get columnar grains, and then you may have dendrites form in the center. And through all this, you get fluid flow in the liquid as it's cooling down. Remember, in a big casting, this could take hours or days to cool down, and the liquid is getting enriched in one of those other elements. So the first stuff that solidifies is very rich. In a ingot cast steel, a rimmed steel, this would be a very pure iron alloy on the surface. And so we could get the best sheet properties from ingot cast steel, okay? Because the surface was very pure iron. The internal composition might be slightly different. You're going to roll it into sheet, you don't really care. But in plate, you didn't want that. So we have to worry about how we solidify these things. But as the fluid flow goes on here, it's due to differences in buoyancy, and part of that buoyancy is the composition differences. I got molybdenum, which is very heavy compared to steel, and in an iron molybdenum alloy I can get tremendous segregation because of the differences in densities of the different elements. And that's what we call macro segregation. If I look, should have some pictures of some macro, here we go. Macro segregation. This is an ingot showing macro segregation. In this case they show it as pluses and minuses. Minus, my alloying element is deficient down here, it's enriched up in here. This is called A segregation. The ones on the outside, the ones in the center are called V segregation, and it's basically just due to fluid flow. But fluid flow among the dendrites. This is fluid flow between the solid limbs of the casting alloy, so it gets sort of messy, okay, to analyze. But people have measured it, and they probably still are analyzing it. But so actually, this one actually shows you some of the terminology. So we get, you have your riser up here, positive segregation in the riser, branch columnar dendritic zone, V segregation in the center in the equiaxis grain zone, negative zone that we saw before. We have a chill zone down here and a columnar zone. So you really have some sort of composite from the original casting. And that's a problem in a lot of cases. You want to break that down, and so you may later forge the product to get rid of it. If you're lucky, if it's iron or titanium, those alloys will actually go through a crystallographic phase change at intermediate temperatures. Iron goes from face center cubic to body center cubic at around 900 degrees centigrade. Titanium goes from BCC to HCP at a similar type of temperature. And you can cycle the material in the solid state and break down some of this stuff. But it turns out if you want to diffuse away the compositional gradients from a big ingot, you can wait a couple of thousand years in a hot furnace. The rate of diffusion of the elements over long distances is so great that macro segregation cannot be annealed out. Micro segregation can be annealed out, but macro cannot be annealed out. So what do? We take something that's got large grains and lots of segregation, and we work it. We forge it, we hammer it down to a smaller shape. You don't use, cast plate. If we could use cast plate, we could save a lot of money. I mean, people make pressure vessels out of 4-inch thick plate. If you could cast it as 4-inch thick plate and get uniform properties, we would, but we can't. If you want 4-inch thick plate, you better start with 16-inch thick castings and get 75% reduction to break up this macro segregation and homogenize it. It's not all that different than kneading dough. It's just we don't kind of fold it over on itself. But actually the old blacksmith did fold it over on itself. Okay, when they had the sponge iron, they basically would literally fold it over on itself, just sort of like kneading dough over and over. Now you oxidize away a lot of your stuff, but nowadays we put it in a big hammer press and we forge a big ingot into a small round. And so if you start out with a 40-inch diameter ingot, you can forge it into a 12-inch bar. Okay, and you can machine things out of that bar. The bar won't have very much macro segregation. But in fact, a lot of the specs will require you to take a bologna slice off the end of that ingot, that 12-inch ingot, and etch it with a special, they'll tell you what type of etchant, to look for segregation that still remains from the original casting process. Now this is not so common if you're making railroad wheels, but if you're making aircraft engine parts, it's very common. Okay, the specification is going to tell you to do a macro etch test. Slice a piece off, make sure that you don't have a lot of segregation. okay? So you have to get it homogeneous. Yes?
So this is a major issue in those generator
Rotors,
rotor
right.
columns, and then
Yeah, those things could be 60, 70 inches in diameter as the ingot, and they'll forge them down, and they may end up at 30 or 40 inches in diameter. But the area reduction is still about, if you go down twice in the diameter, you get 75% in the area. And in general, you need about 75%. You'd love to be able to get 90%, okay? This particular ingot, which actually has a little bit, very small amount of silver, like 0.1%. This, I was brought in because this was going to, did I tell you, this was going to be the trolley wire for the Amtrak New Haven to Boston extension, okay, the overhead line. And the company that was making this wire, the largest wire, diameter wire they had ever made was 5/16 of an inch diameter. And they had made it from this 1 3/8. Now this starts out as a very large grain. This is not segregation here, but it's the grain size. And if you look at properties of metals in general, this is steels, this is aluminum, this is copper, this is virtually everything. You can add alloying elements and everything as much as you like. I don't know if what I'm going to draw here, but you have what we call strength. Well, strength and toughness are the two properties that we're interested in. And strength is the force of fracture, okay? I'm just going to measure how much force it takes to break something. And so we talk about the yield strength of the material, and it has to meet some minimum value. Toughness is the energy of fracture. Glass is actually fairly strong. It's actually stronger than steel. That's why fiberglass composites can be reasonable strength. The fibers are stronger than steel, but they're not very tough. They shatter, they're brittle, there's not a lot of energy. And in fact, actually what I can plot here is stress versus strain. And you go up, you yield, this is sigma y for yield, and it may keep on going up to some sigma u for ultimate tensile strength, that's the maximum stress, and then it'll break. Well, the area under this curve is the energy that it took, force through a distance, if you will. Stress times strain is the work necessary to deform this bar of metal, or this piece of rubber, or this piece of glass. Well, glass has a stress-strain curve that looks like this. There's no area under the curve. No energy of fracture in glass. It's a brittle material. It doesn't stretch. Rubber, on the other hand, doesn't have much strength, but boy, it stretches, and there's a lot of energy under that stress-strain curve for a rubber band. You can shoot it across the room. You try shooting a piece of glass across the room, okay? Can't store a lot of energy in it. So the one thing in metals that will give you both strength and toughness is fine grain size, okay? You want both. The Liberty ships taught us you want toughness. We knew about strength in 1880. That's when they first started doing tensile tests. And that was the specification until the 1950s. After the Liberty ship problem, they basically realized research at Naval Research Lab, British Welding Institute, and MIT were actually the three places in the world that really did the study of the brittle fracture of steels, which was the Liberty ship problem, and found you needed to include toughness, the area under the curve. You wanted ductility. Last week I was down at the Army where they're making armor and stuff, and they say their three metrics are strength, toughness, and ductility. And ductility. Well, this strain is ductility. Stress is the same as strength. Well, what's toughness? It's just the area under the curve. So what I wrote up in my report, it's nice that they have these three metrics, but only two of them are independent. Okay? If I got an area here, the area is just equal to the length times the width, right? So you only need 2 of these to define your strength and your toughness, which are the 2 things you want. But they like to measure all 3, okay? But I'm not sure they've thought it through enough to realize that only 2 of the 3 are independent. But nonetheless, so what happened here is they had the large grains to break down this grain structure in a very pure material like this copper. They were supposed to go from this cross section down to about 560. So that would be about an 80% reduction. In order to get the strength and the fine grain size and the ductility, they really needed about a 90% reduction. But their continuous caster couldn't make anything any larger than this. They had never made wire. This was twice the diameter, 4 times the cross-sectional area of any wire they had ever made. And I had 2 days to decide whether to accept $6 million worth of this product or reject it. And I rejected it. And then they sued the government. And when they sued the government, you don't sue the government unless you're squeaky clean. Okay? It turns out the contract, because Amtrak's owned by the government, right? So the contract for this stuff basically said the government put certain specifications on the strength and the ductility of this trolley wire. This is the trolley wire right here. Okay? It's going to start at this diameter. It's going to end at that diameter. It didn't have a 90% reduction in area. It only had about an 80%. And their wire didn't have enough ductility. The real problem is because it still had large grains. It hadn't been worked enough to get to small grains. It actually wasn't very smooth on the surface. It had little waves. But when you're going 100 miles an hour, little waves become big bumps. Okay? And so when they tried to run the train down the track, it was like the 4th of July with the sparks coming off as it bounced along the conductor. Okay? And of course, if you had those arcs, this thing would have worn out within months. Okay? So anyway, I rejected it. They countersued because they had a fixed price contract and they could have made an extra few $1 million if they had been able to buy this stuff from this one small firm. And they had justified going to that firm because they said, we tried to source everywhere in the world and no one else would bid on this specification, which wasn't true. They were lying. Phelps Dodge, the 2nd largest copper company in the world, headquartered in New Jersey, had been begging this company, this British company who was building the extension, had been begging them to let them put in a bid because they had a new process that had what we call redundant deformation, and maybe when we get to deformation, I don't know if we'll get there, but basically it really needed the metal. It really worked it over, okay? In fact, this is one of the ways the Army's looking at some new magnesium armors now, the same conform process that was developed in one of the British labs, where you really get a lot of work into the metal and get very fine grains. They actually had made something that was too ductile. That's what the company said. Well, your material has too much ductility, too much toughness. It's too good for us, so we won't let you bid because you don't fall within our spec. This is what they said. And then they turned around and told the government that this other company was a sole source and they had to use their material. And then Tom Eager came around and rejected it. And so it turns out once they rejected it, it's going to slow up a $300 million project. But all of a sudden now the government said, well, why don't you go to Phelps Dodge? Because we understand they were interested. Well, it turns out when this thing went to the lawsuit, the company came in with their technical argument why Tom Eager was wrong, okay, on the properties of the material. The government came in and said, you just defrauded the federal government. They yanked the passports of the British managers, took their computers, and basically turned it into a criminal trial. Okay, so you don't fool around with people who bring in, actually it wasn't the FBI, it might have been the FBI that came in, but anyway, it's a long story, but the story's a little bit longer than that, but That's basically what happened. And when they saw the legal response from Amtrak, they all of a sudden they realized they had committed a sin, and they were in trouble. So, but anyway, it turns out the wire that went up was the Phelps-Dodge material, and it's great material, great ductility, great strength, great toughness. Okay, it's got all the properties we wanted and more. Okay, but that was why it was defective according to the British. Of course, the real thing the British was looking at, it was $2 million cheaper, okay, on a $6 million order. And so they decided that would be great material. This junk would be great material. Except that was another thing they did. Amtrak sent them an order, said, do not put any of your junk material up. And they did. Right down here in Providence, they put up about 6 miles of track with this wire. And that's the way we knew that it would spark, because they ran a train down. It was just the 4th of July all over the place. But that was their big mistake, because it wasn't clear that I could back up with data my assessment that this material wouldn't be as good enough. Okay, but once they ran it down the track and you saw it sparking, we all knew it wasn't good enough. It became obvious it wasn't good enough. But until they ran the test that they were told not to run, okay, we didn't have the data to really back us up. But anyway, so sometimes I luck out. Okay, any questions on any of that? Okay, I think that in fact I know right now that I'll be here Thursday. I won't be here tomorrow, I gotta go to Washington. But I should be here Thursday, and actually Thursday we're gonna go through some forging. I don't know that we're gonna get to rolling or powder metallurgy. You'll just have to take this course in the fall or some other time, or just ignore it for the future. But that will be the 12 extra hours. This is the 5th class, and Thursday will be the 6th class, and we've been two hours a time. So I'll still be around. Maybe I'll come to a couple of the classes and watch the videos or something. See if I still believe what I said back then. Okay? So I'll see you Thursday.